Mean free path. What we mean by mean free path is how far a molecule will travel before it runs into something. The things it can run into are another gas particle or the walls of the container. So gas molecules go in straight lines until they run into something. It's a little bit like that original video game Pong. You guys at least heard about Pong, right? That was so cool when I was a kid, right? So it was this little blip on the screen, and it would just go in a straight line till it ran into the sides of the screen or to your little paddle at the bottom, and you just move the paddle left and right. It was like, so simple. It was crazy fun, though. And you try to keep it going, right? So I think of gas particles a lot like the blip in Pong, except there's a whole bunch of them going, and they can bump into each other. So mean free path, how far they go before they run into something. As you increase the pressure, you squeeze those particles together, the mean free path is going to decrease, right? Because they're more crowded together, they're going to run into things. So the mean free path decreases. Again, with the golf ball analogy, if nitrogen was the size of a golf ball, it would travel about 40 feet before it ran into anything. So we talked about there being, for argon being about 4 feet in between, and you've got these particles, and they can, on average, travel about 40 feet before they run into each other. That's on a scale that we could see. So here we see a box with gas particles in it, and we're watching this one, and it runs into a particle, it runs into a particle, it's running into these different particles, right? And it can also run into the side of the container, like here. Okay? So there are two processes by which gases can spread out. One is diffusion and one is effusion. So diffusion is the more common one. Diffusion is when the gas particles move from a high concentration to a low concentration. Gas particles, what they'll do is they will naturally expand to fill whatever container they're in. They do that by diffusing. Heavier particles are going to diffuse more slowly because the heavier particles have lower velocities. In order for them to diffuse, they have to move around until they uniformly occupy the container. Effusion is a process in which a gas escapes through a small hole into a vacuum. So that's not as common. But the rates of diffusion and effusion are both related to that root mean square velocity. If the velocity is faster, the rate of diffusion is faster. If the velocity is faster, the rate of effusion is faster. And we know that the velocity is related to the size of the particle, the molar mass. So the rate of gas movement, either effusion or diffusion, is inversely proportional to the square root of its molar mass. And you can derive this equation, and if you're interested, I think the book goes through some of that, but I know that most of you are not interested, so bang, there's the equation. So this is Graham's law of effusion, and here's an illustration of effusion. So here we have a box that contains a partition in the middle. Originally, on the right side is a vacuum. There are no gas particles here. On the left side, we have a gas, and of course that gas is going to have some sort of a pressure. We have a single hole in the middle of this partition. That hole is large enough for a gas particle to fit through. Now, I don't know about you, but what I would think would happen is that this being a vacuum and this being a pressurized gas, I would think of like this sucking all the gas particles in, or these, squeezing out. But that's not actually what's happening. What's happening is you've got these particles, and they're like, oh yeah, there's that vacuum over there, we don't care. They're just bouncing around like they bounce around all the time, until one of them happens to score a direct hit on the hole. It hits a direct hit on the hole, it goes through. Now it's on the other side, and it's going to be bouncing around. The rate at which the gas moves from the pressurized side to the vacuum side depends on how fast the particles are moving. The faster they're moving, the more frequently one will score a direct hit on the hole. But they don't get sucked out. They're just bouncing around. It's really kind of crazy to think about. So we can look at, yeah, question?
Could it go back though?
It could go back, yes. So you've got a couple particles over here now bouncing around. Could one of these score a direct hit and go back? Absolutely, it could. And eventually what's going to happen is you're going to end up with an equal number of molecules on each side, equal pressure on both sides. So when we talk about rate of effusion, we're talking about a vacuum on this side. So if we watch this container for a while, this isn't going to remain a vacuum very long, right? Because technically, as soon as one particle goes through, then it's not a vacuum anymore. Because as you get more molecules over here, then you also have them going back in the other direction. So the rate of effusion of two gases is equal to the square root of their molar masses, but that ratio is upside down because faster means smaller molecule. Slower means larger molecule. So there's this inverse business going on here. So find the ratio of effusion rates of hydrogen gas and krypton gas. This is an equation that I will provide you with. We just don't use it that often. So I don't think it's really worth spending a lot of time memorizing. You do need to know what the capital M means and how to use it. And it won't be labeled. It'll just be an equation on a piece of paper on your exam. Exam 3. So ratio of effusion rates of hydrogen gas and krypton gas. So we need that effusion equation. So the rate of A, instead of A, I'm going to use hydrogen. The rate of hydrogen effusing to the rate of krypton effusing would equal the square root of the ratio of their molar masses. But hydrogen's going to be on the bottom and krypton's going to be on the top. Okay, that's too frustrating. Okay. In the root mean square velocity equation, these had to be in kilograms per mole, so that they would cancel out with the joules that had kilograms hidden inside of it. Here, when we've got one molar mass divided by another molar mass, the units are going to completely cancel out. So you can go ahead and convert those to kilograms per mole, but you can also just use it in grams per mole because the units are going to cancel out. So I'm going to use grams per mole. So the molar mass of krypton is 83.80 grams per mole. The molar mass of hydrogen is 2.016 grams per mole. And we have to take the square root of that. It's the square root because this is related to the velocity. Kinetic energy is the mass times the velocity squared, and that's why we got the square root in there. So the units, grams cancel and moles cancel, and this, because it's a ratio, ends up not having any units. So the square root of 83.8 divided by 2.016. 6.447. No units. 4 sig figs on the top, 4 on the bottom, so I rounded it. What that tells me is that hydrogen gas will effuse 6.447 times faster than krypton. Make sense? It's the ratio. You might say, well, that doesn't look like a ratio. Well, it's per 1, or 6.447 colon 1. Yes?
I think it's just that, like, on the left is the rate of hydrogen over the rate of krypton, and once it's in the square root, it flips.
Right. Because the rate of effusion is proportional to the velocity, right? And the velocity, we called it the root mean square velocity, was the square root of 3RT over the molar mass. Yeah, that's why it's upside down. Any questions?
Did you put hydrogen on the top on the left so that it could be on the bottom because it's a smaller ratio?
That's a good question. Why did I put hydrogen up here? I mostly did it because hydrogen was first in the problem. Yeah, but it does end up being usually in a ratio. We like a ratio of 6 to 1 instead of 0.25 to 1, right? So it ended up working out that way. Yeah.
So on the test, what we do, just do it first, put that one on top, and then the one after.
On a test, they should word the question more carefully, and it should tell you, find the ratio of effusion rates of hydrogen to krypton. It should specify, yeah. Because otherwise, yeah. Any other questions?